So the different molecular orbitals that you can form obviously have different energies, right? And then this is going to be very important in making molecular orbital diagrams and coming up with the overall energetics of any system that you care about. And so we're going to go over some guidelines of how to order the any given set of different molecular orbitals. And so the first is that bonding molecular orbitals will lie lower in energy than the anti-bonding molecular orbitals formed from the same atomic orbitals. And non-bonding molecular orbitals will lie in between. So this is always true. Take a very simple example, in fact, the simplest example possible, where you're making hydrogen from two individual 1s orbitals of hydrogen atoms, right? You got one electron in each of these, and you're going to make an anti-bonding orbital by adding the two 1s orbitals destructively, and a bonding orbital by adding the two orbitals constructively. And there's no non-bonding orbitals in this case, but the anti-bonding orbital is higher in energy. Something that is very important, and a principle we'll be using quite a lot throughout this chapter and the next, is that anti-bonding molecular orbitals are raised in energy more so than the corresponding bonding MOs are lowered in energy. And so what that means is if you kind of have this central line here where my cursor is, that's the starting point, right? The starting energetics of these 1s orbitals. And the amount that this anti-bonding orbital goes up in energy, it's always going to be more in energy than the amount this bonding orbital went down in energy. And there's a very simple thought experiment that you can do that proves to you that this must be true, okay? And so in other words, delta E antibonding is greater than delta E bonding. Here's the thought experiment. Suppose you're trying to make diatomic helium. Now, we all know that this molecule is not stable. Helium's a noble gas for a reason, right? But suppose you try to do this, you're gonna have 2 electrons in each helium atom. And so now you have 2 electrons each, and you're gonna put 2 electrons in the bonding orbital, 2 electrons in the anti-bonding orbital. And the way this is written correctly, with the anti-bonding orbital being raised up higher in energy than the bonding orbitals raised down, or lowered down in energy, you're going to have a less energetic system overall, right? Because the energy of this system right here, when it's 2 atomic orbitals, is right here, but the energetics of this system is something higher, right, on average, because this one is higher up. So this kind of thought experiment shows that, you know, an anti-bonding orbital must be higher in energy, how much it was raised, the delta, compared to the delta bonding. Another energy ordering principle is that the strength of orbital interactions goes as a sigma bond is stronger than a pi bond, is stronger than a delta bond, which is stronger than a phi bond. And we'll talk about what these bonds are, but you know, more overlap means stronger interaction. So that's going to stabilize your bonding interactions more. If you have more overlap, they're going to be pushed down lower. But at the same time, that's going to rise the anti-bonding up even more as well, okay? And so you can see, like in this situation where you have 2 p orbitals, those lobes can really interact. There's a lot of interaction there. So that would be a lot of overlap in a sigma bond, but that would be a sigma bond. And why this is a sigma bond, we'll get to in a second. It has to do with how many lobes are interacting. So we'll get to that in a few slides. Here's an example of kind of medium overlap. It's still a sigma bond, but you have an s orbital, so that's kind of more more diffuse, and a p orbital, which is very directional, so kind of medium overlap. And 2 s orbitals, they're kind of diffuse, you know, spherical. Electron density equally probable on the right side, where there's not a bond for this orbital, for example, and on the left side where there is a bond. So that would be a weaker type of sigma bond, but still a sigma bond. Then you go down to a pi bond, and that's going to have smaller overlap, and a delta bond, and lastly, a phi bond would have even weaker overlap. So what this looks like, right, is if we just kind of have a generic sigma bond, that's going to be the most stable energy, and the corresponding antibond is going to be the least stable, because that's very strong destructive interference. So that's highly unfavorable. You have lots of negative overlap there, or opposite sign overlap. Okay, and then the pi bond, if you had a pi bond in the system, that would be stabilized next, but not as much from where the p orbitals from which it came. And then that pi antibond, right, where the signs are reversed, that would be right here. And then here would be your deltas. Your delta bond would have some stabilization, it's a very weak bond, and your delta antibond would also have some destabilization. So how do we define different types of bonds? It has to do with the number of lobes of each atomic orbital interacting. So you might have certain preconceptions about this. You think of a pi bond in organic chemistry, you typically think of p orbital, right? I mean, that's really the only P's and S's are the major players in bonding in organic chemistry. But that's not the definition of a pi bond. You can have pi bonds with d orbitals, with f orbitals. You can have pi bonds between a p and a d, for example. And you can have a sigma bond with a p, or right, or with other orbitals as well. So it has to do with the number of lobes of each atomic orbital interacting. So these are all examples of sigma bonds. One lobe of each atomic orbital interacts. One lobe with one lobe, sigma bond, interacting. One lobe of p, one lobe of s, interacting, sigma bond. One lobe of p, one lobe of p, interacting, sigma bond. One lobe of d, one lobe of p, interacting, sigma bond, okay? Pi bonds, you have two lobes of each atomic orbital interacting. One lobe of p, one lobe of p interacting constructively, but a second lobe of p and a second lobe of p interacting. Two lobes from each p orbital are interacting. That's the definition of a pi bond. Two lobes of each atomic orbital interacting. One lobe of a d, one lobe of a p. Second lobe of a d, second lobe of a p. That's a pi bond between a d and a p. First lobe of a p, of a d, first lobe of a d, first lobe of a d interacting. Second lobe of a d, second lobe of a d. Two different lobes interacting. That's a pi bond between two d orbitals. Delta bond, you may or may not have heard of this. This is a weaker bond, but it's been experimentally confirmed in a wide range of inorganic complexes, transition metal complexes. So you can make, for example, metal-metal bonds that have these delta bonds, and we'll talk all about this in a bit. It's pretty fascinating stuff, and really kind of blew up people's preconceptions about the limits of bonding, sort of in the 1970s, where a lot of this was discovered. And so a delta bond would be something like this, where you have one lobe and one lobe interacting, a second lobe and a second lobe interacting, a third lobe and a third lobe interacting, and a fourth lobe and a fourth lobe interacting. Four lobes of each atomic orbital interacting, that's a delta bond. And lastly, there's a phi bond. Phi bonds it looks like exist according to modern day computations. It's thought to be important in the diuranium molecule. Okay, it's a very weak type of bond, and it can happen between two f orbitals where you have 6 lobes. So you can see there's 6 different lobe-on-lobe interactions here. That gives rise to a phi bond. All right, so these are all different things we will be using to be ordering the energy of MOs. And the last thing is looking at the number of nodes. And so the energy of molecular orbitals will increase as the number of nodes increases. And so you can see here at the bottom, all of these are sigma type interactions, right? One lobe, now we have 3 different sites. So it's like 3 different atoms, right? 3 different orbitals, but it's one lobe on one lobe, one lobe on one lobe, one lobe on one lobe, one lobe on one, right? But you can see, how would you order these? You would just look at number of nodes. And so a node is anywhere the sign changes. Bottom one has no nodes, the top one has 3 nodes, and more nodes you have, the higher the energy. Basically, you have more anti-bonding interactions when you have more nodes. Okay, so next what we're going to talk about in the next video is, now that we know a little bit about how atomic orbitals can overlap, we're going to talk about the multiplicity of bonds and what distinguishes a single bond versus a double bond, etc.